Good evening, everyone. This is our second talk in this week, and today we have one of our own, Berkay Köprü, who is a PhD student in the Multimedia Vision and Graphics Laboratory, working with Engin Hoca. Let me just briefly talk about his background. He got his BS degree from Bilkent University and his master's degree from TU Munich. His research interests include human-computer interaction, computer vision, and affective computing. And today he will talk about his ongoing PhD work on the use of affective visual information for summarization of human-centric videos. Thank you, Berkay. The floor is yours.
Thank you, Aykut. So for the introduction, good afternoon, everyone. As Aykut presented, I'm a PhD candidate supervised by Professor Engin Erzen, and we are currently working on the intersection between affective computing and computer vision. And today I will try to present one of our recent work in that area, which is the use of affective visual information in summarization of human-centric videos. So let's move on to the next slide. Okay, so here is my outline. I will start with a brief introduction, defining the video summarization task and why affective information and affective computing help to the video summarization task. Then I will present the continuous emotion recognition module, which is the one extracting the affective information. Then we will dive into the enhanced video summarization for human-centric videos. In the results part, we will discuss the performances of the proposed architectures, and I will wrap up everything in the conclusion. So video summarization, what is it? Given an input video, the goal of video summarization is to create a shorter video that captures the important information within the input video. And basically, it has two categories, which is selection of key frames or selection of key shots. The difference is in the selection of key shots, we are selecting consecutive frames, while for the keyframes, we are selecting independently the frames. And in this work, we focus on the first one, which is the keyframe selection. And the importance of video summarization is come with the video content search, especially from 2017 to 2020. The content search from the usage of the video content search for quadrupled in that domain, and currently we have seen 500 hours of video upload per minute, and especially user-generated videos allocate the major part of the available videos among the video streaming platforms like YouTube, Twitch, and Instagram. In regardless of their category, whether it's news, cooking, commentary, we have seen that these user-generated videos are human-centric. And to depict that, I just captured the trending videos from 2 different days in Turkey. And we have seen that like all these videos are human user-generated. They are no more than, they do not involve more than 4 or 5 people. And as you can see, there's also like mostly like it's like a selfie cam based videos. So by regarding this search, the compact representation of these videos become more important, and existing solutions neglect the effective content in these videos. As human beings are both emotional and cognitive beings, while the emotional part is driving the ladder, which is the cognitive part. Hence, we believe that by extracting the effective content in these videos and feeding them to the video summarization frameworks, we can achieve better performances for human-centric videos. So I will start with a brief snapshot of how our overall architecture looks like. Basically, it includes two steps. The first one is to come up with a module which extracts the effective information, which is the continuous recognition part. Then, during the second part, the training of the video summarization, we try to feed this information into either encoder or decoder or both. And current architectures that we explore, they consume the whole video at once and provide the outputs at once as well. So the output of the video is a sequence of binary labels, whether we include a frame to the summary or not. So let's start with our continuous emotion recognition module. Before diving into what we are doing in that module, I will briefly try to explain what are affective states and what are emotions. Affective states are consist of arousal, valence, and dominance. These are representative of how much we are active or passive for arousal, how much we are positive or negative, which is valence, and how much we are dominant, which is dominance. In this work, we consider only arousal and valence, and also in the right, I depicted how emotions reside in this two-dimensional space. Basically, the emotions are a portion of this two or three-dimensional domain. So after having the information that we need about what are affective states, I would like to briefly mention how our continuous emotion recognition module works. So first of all, we play with the frames, and we do that in order to, by considering the slow varying nature of affective states. The affective states, the emotions, they tend to change slowly, and by considering this information, we think that consecutive frames, they do include low extrinsic information. So in order to increase the receptive field size of our network or our module, we skip frames. And this is actually mimicking the diluted convolutions. But instead of doing that after fetching everything from the memory, we do it before. And this is by doing so, we really enlarge our receptive field size for longer domains, which can capture this slow varying nature of the problem. So by considering this, how we play with the input, we create a window of frames representing time of interest, and each of these frames are passed from GoogleNet, which is trained for image classification. But what we are doing is we are extracting the output of pool 5 layer and pretending them as visual features to estimate, to regress the arousal and valence. After we created this sequence of window of features for time of interest, we pass them into a couple of convolutional layers, and then a GRU layer to follow sequential nature, and also to follow the longer dependencies. And there's a hint there. We do not only estimate the arousal and valence, which is the output of fully connected layer, but also extract the output of GRU layers. And in that sense, we would model the affective information in twofold. One, which is the estimated arousal and valence, and the other are the output of GRU, so to say, GRU embeddings. And this network is trained with concordance correlation coefficient, because the affective computing field, they measure the performance of the systems using this this coefficient. It's basically a correlation coefficient, also penalizing the mean differences between the estimated and reference values. So by taking that, let's move on to how we fuse this information, affective information, in the twofold. So again, so our approach is we would like to fuse this affective information to enhance the summarization of human-centric videos. But what does it mean for us to summarize a video? So currently we have a sequence of frame representations which are the outputs of GoogleNet as visual features. Then we would like to assign a binary class label to each frame, where the positive class means we are including that frame to the summary. Okay, so I mentioned that we would like to fuse this information. Hence, we choose a baseline for our model. And this model is from video summarization using fully convolutional sequence networks, which is published in 2018. And this paper actually uses the fact that semantic segmentation and video summarization has similar nature, because basically in the video summarization, we are trying to find salient regions and a background, which is in the semantic segmentation, the salient regions are kind of objects, and we are trying to remove it from the background. So, now I will show our first two proposed network and the baseline. The baseline, which is SumFCN, is only using the features from GoogleNet. So it extracts the features from the GoogleNet. It passes a fully convolutional encoder. There's a bottleneck. And then the temporally compressed information is the convol to find the binary class labels for the baseline. So initially what we do is we try to see the effect of early fusion of the affective information that we are extracting. And initially we tried the affective attributes, which are arousal and balance, and in another experiment we tried the GRU embedding. So like we are appending these additional features to the output of GoogleNet, and then actually we see that the GRU embeddings are working better. So like most of our proposed architectures are on with the GRU embeddings, and I will mention why we have done such a design choice and what's the reasoning behind it in the results section. But as you can see, the one is a simpler early fusion manner, and the other one, the skip connection AV, it enforces the effective attributes to the output and try to estimate the binary class label after that. So we have an early fusion, early plus late fusion here, and then we try to look for how we can do the fusion and employ attention. So our first idea was to temporarily attend to the frames so that salient regions would be positively weighted or get a higher weight. And that's why we had an multi-headed self-attention at the bottleneck for the temporal attention-based awesome architecture. Again, as I mentioned, now we are only using the GRU feature, the GRU embeddings for the appendment in the input. So like the second concept that we explore the use of attention for the late fusion. So we use the idea from sequence and excitation networks to spatially attend regarding the similarity between the affective features and the output. And that's why we employ an attention to the output where the query is coming from the embeddings from the GRU. So that would be, so we are trying to stress the effective information there. So in total, we have four new architecture, and we train all of them are trained using weighted binary cross entropy. As I discussed, our main purpose is to come up a sequence of binary labels for each frame. So let's move on.
Berkay, can I ask a question? So here there is this multi-headed attention layer and the self-attention layer at the end. So are these cross-modal or not?
No, they are not cross-modal.
Okay, so I'm just asking this possibility of, so there are these different versions of multi-head attention or self-attention where the queries or the keys can come from a different modality. So maybe in your case, you can also explore that possibility.
Okay.
Did you get what I mean?
Yeah.
But you have these different encoders for these different modalities, the visual modality and the emotion related. Maybe you can use one of the features from this to modulate the other.
Yeah, for this second architecture here, actually we are almost doing that, right? So like we are using the GRU embeddings with the something that we fetch from, and it makes sense to combine like other different modalities that you mentioned for the queries and keys to further suggest the similarities.
Thanks.
Okay, now let's move on to next slide. So I will try to show the performance of modules that I presented up to now. So we will start with the continuous emotion recognition module, which we named CRNet. As I mentioned, the performance of this kind of modules are measured with concordance correlation coefficient. And we have two attributes here, the activation and the valence. First, we compare our module with one of our previous work, which only uses visual information again. And we've seen that it has stronger performance. And also we compare it with one of the state-of-art module, which only uses again visual information to estimate these values. And we have seen that it has a competitive performance for activation and valence. But here, since our aim was not to get the best CRNet or continuous emotion recognition module, after some experiments, we just stop and try to explore how it affects the video summarization for the human-centric videos. So let's move on to human-centric definition. So now I need to mention that we have conducted the experiments for the continuous emotion recognition in an affective dataset, which is called Ricola. But none of the video summarization datasets, they do not include affective annotations, as it would be normal. And that's why we are doing an data set, we are although training in one, we will be estimating in another, which is a well-known data set for video summarization, TV-sum. And this data set, we need to have an objective human-centric definition, as these data sets are diverse and heterogeneous. It includes like videos involving only cats or dogs. Anyway, so we argue the fact that a highlight of a human-centric video should contain frames including faces. And so we base our human-centric definition for using that actually. So the number of faces, so we threshold the number of faces in the summary to state that whether a video is human-centric or not. And we capture the faces at the videos using a histogram of oriented gradient-based approach. And then we said that for this data set, if we have more than 80 frames in the summary, including faces, we can call that as a human-centric. And that means we have 15 data set, and the demography of this data set is depicted here. At the left y-axis, we are providing number of faces in the summary, and we have sorted them regarding this feature. So and now we come up with a term top L, and whenever you hear top L or a subscript with 15, you should think that the videos are sorted regarding their number of faces, and top L means top L videos including highest number of faces. So now using these definitions, I would like to present the evaluation metrics. The video summarization itself has since it's a classification, it has these traditional metrics, which is the average F1 score among the videos. But since we are introducing new terms for our work, we had to come up with new metrics that shows what's happening at the human-centric videos. And there are two metrics that we have defined, which is top L cumulative F1 score and the face recall. So I will briefly mention what are those. The term itself is a bit, let's say, confusing, but we should attack it as a C code. So like we will start from right-hand side. So we are trying to sum the F1 score differences from the baseline. So we are trying to see whether cumulatively there is an improvement among the videos or not. And that will show us whether in total, in the whole data set, the algorithm is performing as we expected or not. And then the face recall. So we define this metric in terms of the summary. So since we are saying that human-centric videos should highlight faces, and so our a human-centric video summarization should successfully catch all the faces in the summary. So following these, since we have introduced these new metrics, now we have a dilemma, because during the validation step, so we generally use this kind of metrics to find the best model for our purposes. And now, since we have defined additional metrics, we explore the behavior of each architecture for two different criteria. First, the usual one, which is the maximizing F1 criteria, and the other one is the one that maximizes face recall. So I will start with the traditional approach. So here we select the models regarding their F1 scores, and the table depicts the performances of the architectures traditionally, and also their performances on the human-centric versions with the 15 subscript. And now we highlight two best architectures at each category. And we see that Awesome GRU, which is the early fusion of GRU embeddings, has promising results for F1, F115, which is at the human-centric ones, and the face recall. And on the other hand, we have seen that Awesome skip connection AB, which is the third one in the table, has the highest F1 score at the human-centric videos, which is kind of expected as we are stressing the effective content at late fusion. So the second unorthodox solution. So now, instead of choosing the model regarding the best, to maximize F1, we are choosing the model, the one that is maximizing the face recall. And similarly, we have seen that Awesome GRU from previous one has a strong performance here as well, which is the second best face recall rate and F1 score here. But interestingly, we had like not strong or strong margin improvements, but here it's a bit different. So the temporal attention-based, which is the fourth column, has a really strong improvements for F115, which is the F1 score on human-centric videos, the face recall rates, and face recall rate at the human-centric videos. And these results actually states us that we have kind of two runner-up methods, which are Awesome GRU and temporal attention enhanced Awesome. And again, we have seen that GRU-based versions are beating the other one, which is the skip connection AV. And we can state that GRU embeddings are superior to the effective attributes as well. And we will try to analyze this kind of claims and our runner-up methods. So let's move on to behaviors of the architectures for the maximization of F1 criterion. So here, what we are expecting from the architectures is to have a better performance until we are losing the effective content, and then we would have a worse performance than the original baseline. And so taking the note, taking this expectation, we inspect this graphic and we see that Awesome GRU, Awesome skip connection AV, and SA Awesome sustains a better performance till top 15. And then actually Awesome GRU, which is the runner-up model, sustains a better performance than the rest. So almost all of the methods are at least behaving as we expected for the human-centric and non-human-centric methods. So now we look into how how these runner-up methods behave at the individual videos. But what we have done is we labeled we divide the dataset into two categories, which is top 15 one and the rest. And so now we are showing the performance of this enhanced architecture, Awesome GRU, against the baseline. And we have seen that the F1 scores is accumulating along the diagonal. And this states that these two architectures are behaving similar, which is kind of expected because we are only playing with at the input. But still, majority of the top 15 videos are on over the diagonal, which means that we are getting some positive improvements. At the right-hand side, we are showing recall face recalls of the same architecture against baseline, we have seen that face recall rates are more scattered than F1 score performance. When we compare these graphics, always the face recall rates are more scattered. So like they are less similar to the baseline for this metric. And we haven't seen a great improvement for Austin-Giroux for the face recall rate, but now we will check the behavior of temporal attention enhanced Austin. So for the F1 score, it's a bit more scattered than the Austin-Giroux, which is kind of expected for us because we are imposing an additional, a big module at the bottleneck of the architecture, which changes things. And especially when we consider its performance for the face recall at the right-hand side, we have seen that most of the 15 videos are either on the diagonal or above the diagonal, which states that which states its superior performance at the face recall. So now, after we analyze the performances among the datasets for top 15 REST individually as well, we were curious on how we can actually explain the performance difference between the affective attributes and the GRE embeddings. So what we did was, in order to understand this, we calculate Kullback-Leibler divergences. But in order to do so, we need two distributions. And we calculated distributions for each feature for their distributions at the face including frames and non-face including frames. And we check their chiral divergence, and a higher chiral divergence indicates a bigger discrimination for the distributions of the feature dimensions across with and without classes. And we have seen that as we see in the performances, GRE embeddings have higher distances in the faces and non-faces distributions. And we believe that this distance at the distribution creates the descriptiveness of effective, let's say, or positive improvements at the human-centric video summarization. So now, like after we have analyzed the runner-up models and try to explain why GRE embeddings are working better, I would like to conclude, try to wrap up what we have did. So we have seen that GRE embeddings are more descriptive than affective attributes and more universal. And we have seen that summarization of human-centric videos requires new metrics because, like with the newly defined metrics, we have seen different behaviors there. Early fusion and temporal attention of effective information brings benefits in terms of F1 score and face recall. And our two runner-up methods, architectures, sorry, Awesome-Giroux has a consistent performance in regardless of the optimization criterion. So it could be used even for the usual traditional versions. But for face recall based optimization criterion, we have attained strong improvements with the TA Awesome. And yeah, this is kind of the summary of what we have done. And if you have any questions, I would be happy to answer.
Thank you, Berkay. Yes, we are open to questions from the audience.
So Berkay, maybe I missed it, but in the conclusion slide, you mentioned that these theory embeddings performs much better as compared to using this effective attributes. What do you think about the main reason for that? So in GRU, you consider the temporal information by accumulating these embeddings through the time domain. Is that the reason, or any other reason that you can think of?
I could add one more thing. Maybe like effective attributes, they are too, let's say, task specific after the estimation. And GRE embeddings are more, let's say, they are more abstract representations of the effective information that resides there. Maybe that's the reason. That was one of our let's say, explanations for that. And the other one is the one that you mentioned, which is having this temporal information as well. And yeah, this.
Okay, thanks.
And I should also mention that there is a data set discrepancy as well. So we would like to extend our work where like we could train this effective where we can extract effective information from more universal data sets, because I guess like the Recola data set, they include videos from which are captured from webcam, which two people are discussing something, while the TV Sum dataset includes many on the wire type videos as well.
So on the dataset side, maybe I can also make a comment. So you mentioned that most of the existing datasets doesn't have this effective attribute annotations. So it's one of our PhD students. We are currently working on query-specific video summarization. So personally, I found the video summarization task a bit or more subjective than any other task we have worked on. So in this query-specific version, as the input, you also specify some sort of a query, which basically guides the summarization process, and you can end up with multiple different summaries of the same video, depending on which query you have used. So maybe one possible way could be to collect these additional annotations and just adapt your approach to this line of research as well. So that might also be a good way to pursue.
And like,
so have you ever heard about query-specific summarization before?
No.
Or query-focused.
Or query-focused.
That's another.
In fact, Aykut Hocam, the next thing that we like to do some data set annotations. So we thought actually we can start with a rich, effective annotated data set and try to annotate it for the summarization task. In order to create just some ground truth for us, do you think actually query-based, if we target a query-based summarization, the annotation effort, could it be easier or more relevant?
I don't think more easier, but definitely more relevant. Like I'm just thinking about just summarize this video, but just show me people which are happy, for example. So there could be many different attributes that might indicate this notion of happiness. So there is also this aspect, the query does not necessarily directly should be one-to-one correspondence with the annotations you have collected, but may have some sort of relatedness.
I see.
Again, the main idea is not to have just a single summary, which is quite subjective, that changes from person to person, subject to subject. So this has more like coherency in terms of collecting the summaries based on specific queries. I think that's the main motivation behind why the task is proposed in the first place.
Yeah, well, when we start checking out actually the effective computing and video summarization literature, we also saw actually works on basically effective observations. They are doing, I mean, they make people watch the video, and during that interaction, they put some emotion sensors to the watchers.
I see.
To annotate the original video that he is watching. So that was the main motivation. We thought that actually, I mean, if really the observer's emotions are important for the summarization task, then maybe we can extract that information from the video.
Definitely that makes sense. Let me just share one example dataset. This is from CVPR 2017. I think this was one of the earliest square-focused summarization work, which also proposed its own dataset and evaluation protocol. So, any question from our students? Gürkan, Canberk, Müge. Okay, then maybe I can also tell it.
Last question will be following in the beginning of the presentation.
So Gürkan, I'm not.
Yes, hocam.
Okay, now we can hear you. Can you repeat?
Okay. Yes, in the beginning of the presentation, it was said that the work has been uploaded to the archive. Would it be possible for them to share the link so that maybe we can further read about the topic?
Maybe like there's a problem with me, but I couldn't understand what you have said.
So Gürkan asked for that archive link to your preprint so that he can read it.
Yeah, sure. Just a second.
I missed a little bit, hocam, so I will try to rewatch and re-understand.
Okay. Thanks. So Berkay, maybe I can ask another question to you. So I also know that some works formulate the summarization process as a reinforcement learning problem. Have you ever seen those works before that directly tries to maximize the F1 score, for example?
Yes. Actually, I have seen them. So like some of them, they define their own rewards apart from it, I don't know. But like, and actually, it could be the fact that we could also maybe define a reward based on effective.
Yeah, that's the whole point. Yeah, you may maybe define some extra additional rewards based on this notion of this effective computing features you are investigating. Yeah. Really interesting work.
In the beginning, like we didn't know, we were not sure whether this effective information would really lead the network, because while measuring the like the amount of information. So the length of the visual features are 1024, and we are appending at most 40 additional features. And we were not sure like whether really these are going to be stressed during the training and all, and that's why we kind of started with a supervised baseline and iterate over that. And now we have more information about how this effective influences the training. I think it's a good direction to go for this reinforcement-based approaches as well, since we know it's kind of working.
Okay, if there aren't any other question, maybe we can stop here.
Not a question, but a comment or a suggestion. So you have this one network for the effective features and one network for the summarization. I don't know if it is meaningful, but maybe you can consider a multitask learning setting where some of the layers are shared between this effective and the network that computes these effective features, and one part for the summarization, because your whole idea is that these effective features are important for summarization. I know it will change your architecture, but just as a comment, I think it could be interesting. Maybe someone has already done that. I don't know.
Yeah, Kutacığım, yeah, that's a good suggestion. In fact, to execute it, we need a data set which is annotated both effectively and summarized. So that is why actually we are trying to create such a data set.
But in fact, you do not really need that. So one batch you can train the effect by using this effective data set, and one batch with the
summarization objective.
I see.
But I don't know. It's just an idea that came to my mind after Berkay's presentation.
I guess like we could do it in the same batch even as well, right? So like just it's an implementation thing. One flow, one data loader, one data set is fetching from one data set, and the other one is from the other, and we will just divert to the right head.
And your next step will be to collect such a data set, right? Yeah.
So we will try to do that first. So it seems it's easier to come up with video summarization annotations rather than having this effective annotations. And obviously there's this usage of more universal. Also, we could, apart from this annotation, we could try to find a, let's say, more universal or on-the-wire effective data set where there is less discrepancy between two data sets. That would be another thing that we think. We are thinking maybe the multimodality as well. These are kind of the extensions of our work that we added to the conclusion of the paper as well.
Okay. Thank you, Berkay.
Thanks again.
Okay, thank you. Then I'm stopping my screen. Thank you for listening to me and your comments to improve our work.
Yeah, hope that you get good reviews soon.
Thanks. Good night, everyone. It's a nice presentation.